We will continue with the next video, which is video class 21. The third application, third and final, last application of Gauss Theorem, that is electric field expression due to a uniformly charged spherical shell. See, this is also surface charge distribution, but the charges will be on a spherical surface. Very important application. We are going to use this situation, this formula in various other calculations in next coming chapters, right? Very important one. The third application, the last one, is also an expected 5 marks question. 5 marks question, very important for your board examination. You need to practice. We will practice, no problem. Now we will discuss how to derive an expression for spherical charge distribution. We will write the expression, students. That expression will be very similar to electric field due to a point charge. What is that? E equals to 1 over 4 pi epsilon 0 charge q divided by r squared. Same expression. I am going to derive, thus concluding the point charge equivalent to charge distribution on the surface. Students, I am putting some charge q over the surface of this conductor. See, positive charges. If I consider positive charges, if I put some charge over the surface of a spherical conducting shell, what will happen? Charges get distributed over the surface uniformly. You are putting the charge over the surface of the spherical conductor, symmetrical surface area, having a radius r, capital R. Now, there is an influence all around. What is that called? Electric field. To find field at a point P, distance r from the center of the sphere. Distance is measured from the center, common point, for both capital R and small r. To find electric field here, what is field direction? As I explained you in the previous examples, classes, the field here is normal, radially outwards. If you consider a point here, to this, there are, for example, you consider a point charge this, there is a corresponding charge here. When you find force due to this in this direction, there will be force in a direction like this. When you resolve the values of these two, you will get field in this direction. The perpendicular components cancel, as I explained you in the previous two examples. The electric field due to a uniformly charged wire and plane sheet. That's why the field here too radially outwards. Why outwards? The charge is positive. If you consider negative charge distribution, the field will be radially inwards. Here, field is radially outwards, students. I explained you why. Remember, field is radially outwards. Let us suppose the value of field is here E. By spherical symmetry means if you consider another point here, the distances from different charges will be same as you measure sitting here. If you sit here, measure distance to all the points. Sit here, measure distance to all the corresponding points. Distance will be same from corresponding charges, right? That's why electric field here, anywhere on the surface of another sphere drawn with radius r, is same. Students, you may be wondering why you have drawn this dotted spherical surface. To apply Gauss theorem, students, you are finding electric field at point P, distant r, small r from the center of the spherical charge conductor, charge shell of radius capital R. To find electric field at point P, using Gauss theorem. What is Gauss theorem? Again, electric flux equals to 1 by epsilon 0 times the charge enclosed. Where is the enclosed charge? For that, we have to assume a Gaussian surface, a spherical surface. For simplification of the electric field in a bit easier way, we consider spherical surface, symmetrical surface. That's why. Now, to find electric field at point P, including this point P, you construct a Gaussian surface, which is a spherical surface concentric with respect to charged spherical shell. Students, to find electric field at P, what do you do? Imagine a Gaussian surface, concentric means having the same center as that of the charged spherical shell. What is the radius of this Gaussian surface? Smaller. Here smaller is greater than capital R. Very simple. What is this? This is Gaussian surface. In your notes, it has been printed as Gaussian theorem. You write off theorem, strike off theorem, and then write Gaussian surface. Gaussian surface, over which you are finding electric flux. How do you find flux over a charged spherical surface, over a Gaussian spherical surface where it encloses an amount of charge? We did in the previous video, that is video 19, to explain you how to find electric flux through a closed spherical shell enclosing the amount of charge, right? You go through the calculation part. What did we do? First we consider a small surface area which encloses an amount of which contains the point P. It contains the point P, and the area of this shell or surface area is ds. What is ds? Area of this. I showed you this type of calculation using a ball, right? So in that spherical ball, football, there are some patches like benzene ring, right? Through each patch having area ds, you found flux first. Then you added flux, electric flux through all the surface areas you consider, finding the total flux. So you consider another surface adjacent to this. One more here, one more here, one more here. You add flux through all the surface areas to find total flux. That total flux through the entire Gaussian surface must be equal to 1 by epsilon 0 times the charge enclosed. That's all. Need to find electric flux expression. Put that value here. Then what is Q? Q is just charge. You are not using charge density, multiplying the given surface area, not like that. The entire charge Q has been enclosed by the spherical surface. It's very easy. No substitution for charge. Straight away you write Q for charge. Only you are going to write expression for phi. That's all our discussion. Very simple, students. Before we move on, you just memorize this much. There is a charged spherical shell having radius capital R. What is charge on this? Small q. And the charges are positive, means electric field is radially outwards at all the points. You are supposed to find electric field at point P, which is at a distance R. For that, you imagine a Gaussian surface passing through the point P, enclosing the charge Q on the spherical surface, which is concentric with the circular spherical charged shell. Spherical charged shell, right? This Gaussian surface and charged shell are concentric. Radius capital R less than smaller, right? That's the idea. Now, to apply Gauss theorem, you need to find electric flux over this Gaussian surface. For that, what have to do? We have to consider a small surface area ds over this Gaussian surface, find flux through that. You just go on adding fluxes through all such areas to find total flux. That process of addition is integration, and you are going to add surface area to get total surface area. We have already done it, right? To write the expression for flux, you start with an explanation as usual, right? You write explanation in your own words. How do you write explanation? Consider a spherical shell charged with a charge value small q, the radius of the spherical shell capital R. To find electric field at point P at a distance R, imagine a Gaussian surface which passes through the point and concentric with the spherical charged shell. That's all. What is small q? Remember, I write some key points. You write the explanation. You just write the explanation, just how I explained is there in my study material notes book. You can go through that. What is q? Charge. Charge on this shell, spherical shell. Charge on this shell. What is smaller? Radius. Radius of Gaussian surface. Radius of Gaussian surface. To find what is capital R? Capital R is radius of spherical shell, spherical charged shell, right? Charged shell. And then what is O? O is the center of the spheres, both the spheres. That's all, right? Now, to find electric flux, you have to consider surface area ds. And by spherical symmetry, you add this point, very, very important point. I put a star here. By spherical, SP dot means spherical, right? Spherical symmetry. By spherical symmetry, spherical symmetry means all points on the Gaussian spherical surface are at the same distance from the center. That is spherical symmetry. Spherical symmetry. Electric field value. Field means electric field. Value is same at all points. At all points. Where? Points on the Gaussian surface. On the Gaussian surface. Gaussian surface. Let it be E. Let us suppose that E, capital E, is the value of electric field over each point of the Gaussian surface. Right, students? Very simple. And now, the electric flux, very simple. First, you have to write flux expression over the Gaussian surface. Gaussian surface. What is electric flux over the Gaussian surface? Very simple. You write flux phi. What is phi? E into ds. What is E into ds? Electric flux at each point is E. Surface area ds. E ds. Actually, you wrote E ds cos theta. Where is cos theta? Cos theta missing here. No. Cos theta is there. Why? Because the normal to the area is parallel to electric field. What is the angle theta? Theta equals to 0 degree. Implies what is cos 0? 1. Therefore, it is E ds into 1. Cos theta is there in the form of 1. You need not write that. This is for one area. You can consider several such areas. There are some n areas. You find or you consider one more area, very similar, then the flux is 2 times E ds. Consider one more, 3 times E ds. 4 times ds. Like that, just go on adding. The process of adding is written like this, summation, or sometimes summation is equivalent to integration in higher mathematics. You can use this symbol or this symbol. Some books use this or this. No problem. Totally adding, summation. Right? Summation E ds cos theta. Even if you write cos theta term, you can give explanation. What do you write? Here, theta equals to 0 degree, which implies what is cos 0? 1. Because E parallel to N. What is E parallel to N? Electric field direction parallel to area vector, normal. Therefore, flux phi equals to, what is that? Summation E ds. As I explained you, by spherical symmetry, electric field value is same. You are not adding that. Therefore, what are you adding here? Surface area. But what is summation ds? If you just go on adding surface area, you consider each time ds, you end up with the complete surface area of what? Sphere. That's why summation ds is total surface area. Total surface area of sphere. Total surface area sphere, which is equal to 4 pi r square. You learned in high school, 4 pi r square. Therefore, students, the total electric flux phi equals to summation electric field E into summation area is 4 pi r square. So, this is electric flux expression. Let us name this equation for flux 1. Very simple. Now use Gauss theorem. By Gauss theorem, very simple. Just you are 2 steps away. By Gauss theorem. Gauss theorem. What is Gauss theorem? Gauss theorem states that electric flux over a surface enclosing amount of charge is equal to epsilon 0 times the charge enclosed. Q is charge, flux, right? This is 2. Use 1 in 2, 1 in 2. What is equation 1, 5? 5 is E 4 pi r square is equal to 1 by epsilon naught into Q. So, you bring this term to a denominator, multiply 4 pi with epsilon 0. Why? Is a constant of electrostatics. That's why electric field E equals to 1 over 4 pi epsilon 0 times Q divided by, write r square below the charge. This is what? Right? Are you familiar with this? Yes, of course. You wrote expression for electric field due to a point charge. So obviously, the charge Q over the surface of a sphere is equivalent to the charge at the center. Even if you put the same charge here, the effect here will be same as that when charge is over the surface of the sphere. Whether you put charge over the surface or at the center, the effect of field will be same, no change. That's why the expression, same expression. This is magnitude form, magnitude form, vector form. How do you write vector form? You write arrow, right? Vector field E is equal to 1 over 4 pi epsilon 0 charge Q divided by r square n cap or r cap, totally some unit vector you write, and you explain the direction of n cap. What is n cap? N cap outwards, outward normal. Electric field is same as n cap when the charge is positive. Electric field is opposite to n cap when charge is negative. That's what you know, very much familiar with that idea. This is electric field expression for a spherical charged shell. When students, when you consider a point P outside the charged sphere at a distance r. So this is case 1. So this is case 1. I'll write here. I remove this and write here. What is that first case? What we did is first case of the 3 discussions here. We're going to consider field at a point, field at a point distant. What is that point? Distant r, smaller from center, that's what I wrote. R greater than capital R, outside the, you can add a word outside, distant R, outside from the center. Outside means R greater than R. This is the calculation part. Students, now we can take up one more thing. What is that? Second point. I'll write second point here. You know this? I'll write second point, very simple. I write second one like this. If R is very nearly equal to capital R. What if R is nearly equal to capital? What is small r? Distance of the point P from the center. What is capital R? Radius of the spherical shell. If both are same, what happens? Then very simple. You, in the place of, I write magnitude form. You can write vector form also. What is that? 1 over 4 pi epsilon 0. That is Q divided by, instead of small r, capital R square. That's it. Small rearrangement. What is that? 1 over epsilon 0 into Q divided by, what is a remaining term? 4 pi r square. Can you recognize this? What is 4 pi r square? 4 pi r square is equal to A. What is A? Surface area. Therefore, E equals to 1 over epsilon 0 into charge by area. What is charge by area, students? 1 by epsilon 0 into sigma. What is sigma? Sigma is surface charge density charged by area. This is another expression. Electric field can be shown to be equal to charge density by epsilon 0 for a spherical uniformly charged shell. When you are just outside this shell, the electric field value is sigma by epsilon 0. Electric field E equals to sigma by epsilon 0 when you are very close to the surface. When you are outside, the expression is 1 over 4 pi epsilon 0 Q by R square, same as the point charge. See, put this condition, R nearly equal to R, then 1 over 4 pi epsilon 0 Q by capital R square, multiply 4 pi with capital R square, which is surface area of sphere. So what is charge by area? Surface charge density, sigma divided by epsilon 0. That's it. Students, you practice this 2-3 times, then you will write on your own, no problem. Evaluating flux and equating that with 1 by epsilon 0 times charge. Very simple. I hope you have understood. You go through this explanation part. This is the third explanation. That's why you need not listen to explanation once again. Very simple, right? You consider a spherical charge shell, charge Q, radius R, center O. To find electrified point P, distance R greater than R. First case, field at a point, distance R, where R is greater than R means outside. You imagine a Gaussian surface which is again a sphere, at a distance, again a sphere, having radius R, center same. Right? Now what do? You actually you find electric flux. What is flux? Flux is summation EDS cos theta. That is why, what is the meaning of that? You imagine this spherical surface, Gaussian surface, to be made up of small elemental areas ds. Over each area, what is flux? EDS cos theta. What is theta here? 0, because E and N parallel. E and N, you can write E like this. E and N parallel. So, when E and N are parallel, what is theta? 0. What is cos 0? 1. Therefore, cos theta becomes 1. Summation EDS, you take E outside as it is constant. Summation ds you write. What is summation ds? Total surface area of the sphere, 4 pi r square. You write that here. Use Gauss Theorem, 1 over epsilon 0 q. What is phi? E 4 pi r square. Solve, you get expression 1 over 4 pi epsilon 0 q by r square. Very familiar. You wrote expression for the point charge. So, what is the conclusion? Electric field at P at a distance R is same as that of a point charge. Means, instead of putting the charge over the spherical surface, put it at the center. Same expression is arrived at. Expression is same for both the cases. Charge at the center, charge on the surface. Now, if radius R is, capital R is very close to small r, in that case, you replace small r with capital R. So, it is q by r square, multiply 4 pi with r square, surface area. So, the expression is q by A 1 by epsilon 0. What is q by A? Charge per unit area, charge density sigma by epsilon 0. That's it, students. There's one more part we will see next. Take up one more case here. What if the point P lies inside the sphere? If you bring the point very close to the surface, the expression is sigma divided by epsilon 0. Now, if I shift the point very close or a bit inside the surface, point P, to evaluate flux, same procedure. Including this point, construct a Gaussian surface which is a sphere, concentric, right? If you draw a concentric sphere, are there any charges inside? No. The charges are outside. Charges always reside on the surface of a charge conductor. That's why no charges reside inside the conducting shell. That's why, what is the Gaussian surface? If you think this, if R is less than R, that is the point here, R is less than R, P lies inside the conductor, that's what I am telling you, lies inside the conductor. Very simple, students. Therefore, charge enclosed by Gaussian surface. Charge enclosed by Gaussian surface. What is Gaussian surface? Another concentric sphere is equal to 0. That is, charge Q equals to 0. Therefore, what about flux? Flux phi equals to 1 by epsilon times Q. So, 1 by epsilon times Q 0, total term 0. Right? Therefore, flux phi equals to 0. When no electric flux, implies no electric field. Electric field also 0. Because what is flux? Flux equals to E dot ds summation, right? E dot ds summation. That is equal to 0. Implies summation 0. E equals to summation ds, right? So area is not 0, area is there. That's why electric field value E equals to 0. That's the idea. So if you cross multiply this here, 0 by anything is 0. Therefore E equals to 0. That's it. Flux phi is summation E ds. That is equal to 0. Right side term is 0. That's it. So students, what do you understand? When the point P lies inside a charged spherical conductor, using that point you construct a Gaussian surface, no charges inside. If there are no charges, then the right side term becomes 0. So what is flux? E ds summation equals to 0. If you send E ds to the denominator, 0 by anything is 0. So electric field is 0. That's all. So electric field inside a charged conductor is 0. That is the conclusion, students. Right? Okay, students, we'll see what you have in your study material about the third application of Gauss theorem that I discussed in detail in this video. The electric field intensity means field value at a point due to a uniformly charged thin spherical shell. Under that we are considering first case. What is that? A point outside the sphere. Look here, there is a point P outside the sphere. To find electric field, what do? You consider a surface having area ds, and the normal is this, normal to the area. And what is the direction of the field? Field is also along the normal. Okay. So the surface area ds and the point is P, very simple. And radius of the spherical charged shell capital R, and charges are on the surface, and it is charged with an amount of charge Q. That's it, students. That's what I wrote and explained the derivation just a minute ago, right? Now you have to write, after writing the diagram, this explanation. What is the explanation? A point P be outside a charged spherical conductor, distance R from the center O. Apply Gauss theorem. To apply Gauss theorem, we have to imagine a spherical surface, this one, spherical surface, outer one, which passes through the point P, with O as the center, R as the radius. That's what I told you. By spherical symmetry, this is very, very important. By spherical symmetry, the electric field E has same value at all points. Very important. You must mention this word. It has weightage. Very, very important word. Then you will go to the next page, students. I will remove this part now. Okay. Now in the next page, by Gaussian surface there, a total normal electric flux over the surface is given by phi E cos theta ds. E cos theta ds. This is what you wrote. And you can write one more step further. E outside, summation E outside, summation as E cos theta, summation ds you can write. And he continues further and says, since electric intensity is along the normal to the surface at all points, as I showed in the diagram, theta equals to 0 degree, cos theta or cos 0 becomes 1. Therefore, phi equals to summation E ds. E into summation ds. E into summation ds. Why? Because electric field is a constant. What is summation ds? Total, if you sum the surface areas ds like this, if you continue, you end up with a spherical surface. The formula is 4 pi r square, surface area of a sphere. Now, according to the Gaussian theorem, phi equals to q by epsilon 0. We have found the value for expression phi, that is E into 4 pi r square q by epsilon 0. Q by epsilon 0, students. Therefore, if you simplify further, the value becomes I write here, value becomes E equals to 1 by 4 pi epsilon 0 Q divided by R square. Q by R square, a little bit smaller this one. You will see clearly in your study material is there. This is magnitude form, this is vector form. What is that? 1 over 4 pi epsilon 0 Q by R square into n cap. Next, another important point, students. Again, n cap is a unit vector pointing outwards. Electric field is in the same direction if the charge is positive, opposite direction, inwards if the charge is negative. As I explained you, we have to remember, right? Now, we'll continue further. And one more point he mentions, thus electric intensity at a point outside the spherical charge conductor does not depend upon radius of the conductor. If we increase the size of the conductor or decrease the size of the conductor, electric intensity around at a point is a constant, does not depend on size of the conductor inside, very very important. So it does not depend on the radius of the conductor size and is same as that of point charge Q at the center of the conductor. This point you underline after you read this. There may be a question, 1 mark, 2 marks. Explain why charge on a spherical conductor considered to be at its center. What is the answer? For both the cases, if the charge is at the center or on the surface of the conductor, electric field expression remains the same, which is 1 over 4 pi epsilon 0 Q divided by R square. That is the explanation. I have that question towards the end of this discussion. Again, I will come to that. Now the second point. What is the second point? If the point P you consider is very close to the surface. See here, students, this is the charge conductor with charge on the surface, right? This is what you wrote. Radius of the conductor is R, capital R. Now you bring the point P from outside very close to the surface. The point P is very close to the surface. In that case, small r nearly equal to capital R. So you replace small r square by capital R square. So it is sigma by epsilon 0. Why? Because sigma is Q by 4 pi R square. What is Q by 4 pi R square? Charge by surface area, surface charge density, sigma divided by epsilon. Another important result, remember this, sometimes we will use. And one more, you put star here, a 2 marks question. The question will be like this. If the point is inside, if we bring the point inside the conductor, there will be no electric field. Why? Explain. The answer is very simple. If you bring the point inside the conductor, there are no charges inside. Now if you draw Gaussian surface, it does not enclose any charge. See, if point P lies inside the charge conductor, Gaussian surface does not enclose any charge. So left side electric flux, what is that? E cos theta ds equals to Q by epsilon 0, where Q is 0, charge 0. Therefore electric field becomes 0. So electric field inside a charge conductor is 0. Very important. 1 marks question. Remember this, students. And last one, that's what I was explaining. Remember these 2 points are also very important for 1 and 2 mark section. The question is, explain why charge on a spherical conductor can be treated to be at its center. I will remove these discussions, right? Very simple. Let me read the question once again. Explain why charge on a spherical conductor can be treated to be at the center. See the answer. Using Gauss theorem, it can be shown that electric field expression due to spherical conductor, this is very important, having charge Q at a distance R outside is same as the charge due to same charge kept at its center. That's what I told you. If you consider a spherical conductor with charge over it, the expression here is what? 1 over 4 pi epsilon 0 Q divided by R square, electric field value at this point. If you consider the same charge at the center, then also the expression same. Whether the charges are on the surface or at the center, expression remains 1 over 4 pi epsilon 0 Q by R square only. So the charges on this spherical surface can be treated to be at the center. That's it, right? Final students, this is about the now the variation of electric field with distance from the center. Very simple. Look here students. Now you use this relation 1 over 4 pi epsilon 0 q divided by r square. You can think of this spherical conductor, right? Spherical conductor, radius capital R. Now you are increasing the value of distance r increases. If you are at the surface, r equals to r. As you move away, r value increases. See, as you observe, there is no electric field at the center. Therefore, electric field curve starts from here some value, that is 1 over 4 pi epsilon q divided by r square. Put the values, you get a value for electric field. Then as distance increases, square of distance, with the square of distance, value of electric field decreases. This is how electric field varies with distance due to a charged spherical conductor. If it is a point charge, starts from here. If it is a charged spherical conductor, it starts from the surface. Electric field starts from the surface, decreases as square of distance. Very important. One mass question, right? This explanation. Remember this much. This completes your first chapter, dear students. Go through all the derivation discussions once again. Be ready. I already solved some problems, right? We will solve some more problems in the next videos along with the NEET and CET. Thank you.